Hi, welcome to AP Calculus for East Aurora High School. Today we're going to be looking at limits calculated both numerically and graphically. Let's start with an introduction here. What is calculus? All of the things that you have learned in pre-calculus will be the background knowledge that you're going to need. We add to that the concept of a limit so that we get the body of knowledge known as calculus. So we're going to see how limits are really important in calculus throughout the entire course. In math, we know that problems can be solved in general in three different ways: numerically, graphically, and analytically, sometimes also called algebraically. Let's take a look at the following function. F of x is equal to x cubed minus 1 over x minus 1. What information do we know about this function? Well, if we think about it, for one, we know that when x is equal to 1, if we substitute 1 into the function, we're ending up with a function that has a value of 0 on top and 0 on the bottom. Remember that that's called the indeterminate form. So that tells us that there's a hole in the graph at x equals 1. We can also take a look at some important points for this function. For example, how about an x-intercept? When we set the numerator equal to 0 by letting y equal to 0, we're going to get x cubed minus 1 over x minus 1, set that equal to 0, and it turns out that there's no x-intercepts for this. When we want a y-intercept, we're going to substitute 0 in for x, so we're going to have 0 minus 1 over 0 minus 1, which is a positive 1, so that tells us that f of 0 is equal to 1. And it does have a y-intercept then at 1. Let's go ahead and use the table feature on our calculator to construct a table of values for this function that will hopefully lead us to some information about the limit that we are looking for. The limit as x approaches 1 of x cubed minus 1 over x minus 1. We'd like to know how this function behaves around a value of x equals 1. So, going to your graphing calculator, if you don't have your calculator with you right now, please pause the video and go get your calculator, and then start it up again. On your graphing calculator, remember that we want to set the table. So we want to press second table set, which is the window key. Please have your it doesn't really matter what your table start and delta table are, because we're going to put the independent variable in the ask mode. So switch it from auto to ask. Now when you press second table, it's going to give you a blank x column, and I want you to put these values in for x. So starting with 0, notice that the middle number is 1 and the last number is 2. Now in general in calculus, we want to go the same distance to the left and to the right of that middle number 1. So just to the left of 1, I'm going to go 1/1000th away from 1, either direction. So that's giving me 0.999 and 1.001. Go 1/100th, so get 0.99 on the left and 1.01 on the right, and go 1/10th away from the center number of 1 and get 0.9 and 1.1. Now, please enter the values that you see on your calculator in the table. Hopefully you got the same values that I got. So I've got 1, 2.71, 2.97, 2.997, then an error at 1 because we know there's a hole there, 3.003, 3.03, 3.31, and 7. Now, what we are specifically looking for is what is happening to this function as the x values approach 1 from the left and the right. When I look at this, I see that on the left side, As I'm approaching 1 on the left, my values for the function are getting closer and closer to 3. I see the same thing as I approach the number 1 from the right side. So what that tells me is that as I approach going this way and this way, my y values are getting closer and closer to the number 3. So we're going to say that numerically, by looking at a table of values, I get a limit of 3. Now let's change our method. We're using exactly the same function, and what I have done is graph this function now on my graphing calculator. You can set up your window the way that I've set it up if that helps you to be able to see what's happening to this function around an x value of 1. So in calculus, we're going to solve for limits numerically like we did previously using the table of values, but also graphically by taking a look at the graph. It's sometimes hard to see on our graphing calculator that at x equals 1, I actually have a hole on that graph. But unless we look really, really close on our graphing calculator, we might not see that hole. It might look like a continuous function. Now to find the answer for the limit, as x is approaching 1 from either side, we want to know what y value our function is approaching. So coming from the left side and from the right side, we see that the y value is approaching the number 3. So therefore, graphically, we're going to say that this limit is equal to 3. Look at the two examples below, and let's try to solve those graphically. For the first one, the inverted parabola, we see that we are trying to find the limit as x approaches negative 2. So I'm locating negative 2 on the x-axis, and I want to say what's happening as x is approaching negative 2, what's happening to my function value. You'll notice that this one doesn't have a hole in it. That's okay. I just want to know what my function is approaching. And for this one, as x is approaching negative 2, it looks like my function is approaching a y value of 4. So the limit for this would be 4. For the next one, I want to approach the number x equals positive 2. So here's positive 2 on the x-axis. Let's see what happens as x approaches 2 from the left and from the right to our function. So if I look carefully, I see that that function value is approaching an answer of 7. Again, this function does not have a hole at that point, and I can still calculate a limit. For our next example, we're going to take a look at exploration that's found on page 65 in your textbook. The exploration says, estimate the following limit numerically by constructing a table and graphically by drawing a graph. So first of all, I'm going to put this function y equals x squared minus 3x plus 2 over x minus 2 into my graphing calculator. Again, I'm using the ask mode under my table feature. And when you do that, please fill in the table of values with the corresponding values that you found on your calculator. I hope that your values corresponded to the ones that I found in my calculator. So when I look at this table of values, I want to see what is happening to the y value as x is approaching 2 from the left side and also from the right side. So when I look at those y values, I see that from either side, those y values are approaching an answer of 1. So we are doing this limit numerically by looking at the table of values. You'll also notice that if we substitute 2 into our original function, the function does turn out to be, again, indeterminate. It's got a 0 on the top and a 0 on the bottom, telling us that this graph should have a hole in it at x equals 2. So what this answer for the limit tells us is that the hole must exist at an x value of 2 and a corresponding y value of 1. That's because the function is approaching an answer of 1 when x approaches 2 from the left and the right. Now what I'd like you to do is please put this graph on your graphing calculator and draw a sketch of that graph. Adjust your window so that you're looking around the number 2. and take a look and see if it makes sense to have a limit of 1 for this function according to your graph. This function turns out to be linear when we graph it, and when we specifically look as x is approaching the value of 2, I see that my y value approaches a number 1. So it does make sense according to my graph that this limit is a value of 1. Again, we can see that there should be a hole at 2, 1. Now, in the reading in your textbook, you should have seen the 3 reasons why limits do not exist. The first reason that a limit would not exist is when the function is approaching different values from the left and the right. So sometimes we will have a function where the left side and the right side do not come to the same value. So when that happens, we're going to have to say the limit does not exist. The second reason that we're going to have a limit not existing is when our function has what we call oscillating behavior. Oscillating behavior is behavior where the function bounces back and forth between a high point and a low point, but it's very difficult to see, and in fact you can't find what the function value is actually approaching because it keeps oscillating. The third reason that a limit doesn't exist is when we have unbounded behavior. Unbounded behavior generally means a vertical asymptote because the graph is going close to positive infinity or negative infinity to either side of a particular x value. So these are 3 reasons that a limit would not exist. All of the examples that we've seen before, we have had limits existing. But for these 3 scenarios, we would then say that the limit does not exist. Let's finish by estimating this limit numerically and graphically. So we want the limit as x approaches 0 of the square root of 2x plus 1 minus 1 all over x. Be very careful when you're entering this function into your graphing calculator. Either get into the part of your calculator where you can enter it as a fraction, or make sure that you put the whole numerator within parentheses. Now, when we set up our table, we want the 0 to be directly in the middle. So we see that that's where our 0 spot goes. I'm going to go 1 to the left at -1, 1 to the right at +1. Then start counting down. 1/10 to the left would be -0.1, 1/10 to the right would be +0.1. 1/100th to the left would be -0.01, to the right 0.01, 1/1000th would be -0.001, and 0.001 on the right. Now, take a few minutes, enter this into your graphing calculator, and come back when you've completed your table. These are the values shown on my graphing calculator. You'll notice that we ended up with an extra error at -1. The reason for that is because when I substitute -1 into my original function, the square root portion of this is not defined. It's a non-real or imaginary number at -1. So -1 is actually not even part of the domain for this function. Now, for the most part, I've rounded my f of x values to the nearest hundredths. In this spot, I went 1 decimal place further because otherwise I wasn't showing as good of a progression. So I see that this limit, if I'm doing it using my table of values, which is numerically, I see that coming from the left side and from the right side of 0, I should be getting a limit equal to 1. Now we're going to check our graph and see if that makes sense on the graph as well. So go to your graphing calculator and make sure that you choose a window that is approaching 0 from both sides on the x-axis. When you look at your y values, you can see that you want to approach +1. So make sure that when you set up your window on this, you're going to have to be looking at the positive values for this function value. So I want my graph to look something like this, where I've got a 1 and maybe a 2 over here. And we'll go from the left at -1 and -2. And then my y values, I do want to look at the part that's probably positive. Set up your window on your graphing calculator. See if you can see specifically the place where our hole is in the graph. And we want to be able to tell what coordinates give us that hole. So take a few minutes to enter this graphically on your graphing calculator and then come back and check with mine. We see that the graph looks something like this. First of all, notice that to the left of the y-axis, the first number that is part of my domain and the first number that will allow me to have 0 or above underneath the radical is going to be a -1/2. So my domain is going to be all x values greater than or equal to -1/2. Next, notice that the hole is occurring at the point 0, 1. It's difficult to see this on your graphing calculator because your axes, your y-axis specifically, is showing up and covering over the hole. So one way of being able to see where the hole is to turn off your axes. You can do that by pressing Second Format on your graphing calculator and go ahead down to where it says Axes and turn them off. That will allow you to see the hole in the graph. The rest of the graph is a decreasing function after the y-axis, but it makes sense that we have a hole in our graph at 0, 1, and that the limit of this function as x approaches 0 is equal to 1. So in class, you're going to be working with quite a bit solving limits both numerically and graphically. Next time, we'll be taking a look at how to solve limits analytically or algebraically. Thanks very much for your attention, and we'll see you next time. Bye-bye.